Alright, let's go ahead and take a look at these solutions. So consider the diagram here given. This basically is some mass oscillating on a spring up and down. So it starts at this equilibrium position, maybe as an initial force causing it to move upward. It becomes fully compressed, this spring does, after which a force is exerted downwards, and again we just see this motion, this oscillatory motion. That should remind us, for example, of some sine wave or cosine wave if we looked through increasing values for t. So here in this case, we suppose that this mass oscillating on the spring completes 40 cycles in 1 minute. Find an equation for the displacement d of t. How will we find this? Well, consider we're given here the frequency for motion. So if we complete 40 cycles in 1 minute, so again we know our frequency is 40 cycles every minute, every 1 minute. And from this value we know then that 40 must equal omega over 2 pi, where we're looking at the form for our equation d of t equals a times some trigonometric function of omega t. So see here I've jumped to find the frequency or the value of omega there, and we'll find here in this case that omega is equal to 2 pi times 40 or 80 pi. Now we need to figure out what trigonometric function I should input here. So we'll have a, which we'll be able to determine by our amplitude here. We can see these distances between an equilibrium position and a maximum position is 2. Distance units, whatever those distance units are, so we know we'll be able to find a equals 2. And we have, again, our omega. The only other thing we need to know is, do we use a sine or a cosine for this object in simple harmonic motion? And we can find this by considering the initial position of our object at times t equals 0. So at time t equals 0, see that we start at a minimum value and we're increasing. So we can tell then that this must be a positive sine function. So we know we'll have some positive value for sine. So we can say that d of t equals 2 times the sine of 80 pi t. And we find our solution. So I'm going to put a box around that. And we can move on then to problem number 2. So problem number 2, we have to consider the vertical position of a buoy in the ocean given by this displacement function d of t equals 2 cosine of 30 pi t, where t is the time in hours. Determine the highest and lowest elevation of the buoy. So to do that, we can consider the maximum over the minimum value d of t takes. Consider the smallest value cosine can take is -1, the largest is +1. So we'll have -1 times 2 for our minimum value, or +1 times 2 for our maximum value. We can also find these just by just considering the amplitude and the equilibrium position. The equilibrium position for this d of t, because we have no plus k or no vertical shift up or down for d of t, we know its equilibrium position is 0, and its amplitude is its displacement from 0, or its maximum and minimum displacements from 0, so that would be 2 above 0 or 2 below 0. For any of these reasons, we could say that the, let's call it d max, would be equal to 2, whatever we're measuring our distance units in, and d min, or the minimum displacement we'll see there, or displacement in a negative direction, would be -2. And we find our solutions for the highest and the lowest elevations the buoy achieves. So say this was in meters, d of t was measured in meters, we would have 2 meters above sea level or 2 meters below sea level as the highest and lowest elevations achieved by the buoy. Let's go ahead and look at part B. Determine time for the buoy to complete 1 cycle of motion. So the time it takes the buoy or any object to complete a cycle of motion, this is the time it would take to complete 1 period, or the value of that period. So what could we find here? We just need to find the period. And we consider the period is equal to 2 pi over omega, where in this case our omega is 30 pi. So we have 2 pi over 30 pi which is just equal to 1 over 15. So this tells us that we will complete one cycle in 1/115th of an hour. So in 1/115th of an hour, we will complete one cycle of motion. So if we complete 1/115th of if in 1/15th of an hour we complete one cycle of motion, how many cycles would we complete in 1 hour? We'll see that would be 15. Now we could just do that by looking at the reciprocal of our period, or by our, just general understanding of motion, and the fact that our period is equal to 1/15th hours. We could also use our definition for frequency, where frequency is omega over 2 pi, in this case 30 pi over 2 pi, which is equal to 15. And this says that we'll complete 15 cycles every hour. 15 cycles every hour. Which again is 15 cycles every 1 hour, if I wanted to be exactly answering my question there. My rate is 15 cycles per hour, and my answer then is 15 cycles are completed in 1 hour. So maybe I should write that instead. In 1 hour, we have 15 cycles are completed. And again, note that's because our frequency is 15 cycles per hour. There we go.